Okay, I think we can get started. So today we're very excited to welcome Professor Binil Starly from Arizona State University. So he's the founding school director and professor in the School of Manufacturing and Systems Networks. His lab is working on technologies that merge the digital and physical world towards both discrete and continuous manufacturing. And he has received the NSF Career Award for research in bioadditive manufacturing, the SME Most Influential Professors in Smart Manufacturing, SME Young Manufacturing Engineering Awards, among others, numerous research and teaching awards. So let's welcome Professor Starly, and we're looking forward to an exciting talk on cyber manufacturing.
Thank you. Thank you, all of you. Thank you for inviting me to this colloquium or your seminar series, the department seminar series. Fortunately, it was spring break on ASU side, which is why I'm able to come this week. We typically also have our seminar series on Friday as well. But again, glad to be here. I did not realize it to be much warmer than I thought. I thought it was going to be colder. It's about the same now in Phoenix, about 70, 75 so far. So today what I want to talk about is the cyber manufacturing. It's really looking at all of the changes that's happening. And if in fact you'll see the name of my school, which is also very unique, and hopefully you will see some sort of research directions that are yet to be pursued. Whatever I show today doesn't mean that the research stops. There's a lot more work that needs to be done in this. So hopefully you derive inspiration from this. But before I get into the research area, I also want to talk about my school itself, a little bit into my school. Mike just mentioned about the formation of the School of Manufacturing Systems and Networks has a unique name. It is a startup school, meaning that it is a completely ground-up startup operation on what we have. And I lead that school, which is almost like a department head kind of position. So just a little bit background in ASU. ASU is very different from many other school structures that you see. We don't have departments within the Fulton. We call it the Fulton Schools of Engineering. There's 8 schools within that Fulton Schools of Engineering. If you look at it, you typically where you would have your computing school, that's where the computing and augmented intelligence, industrial engineering is one of the department's programs under that school. And then there's mechanical engineering, which is in the School of Engineering, matter, transport, and energy. Not really mechanical, but mechanical is somewhere inside there kind of thing. So we are organized by the school structures. And one of the reasons why it is organized in this very different way, it's because ASU is about 32,000 engineering students. So you cannot have the same standard departments to kind of do this. We are a very small school, so our school is here, the School of Manufacturing Systems and Networks. You can see just by the number of programs we have, very small compared to some of the other schools. But most of these schools are in the Tempe area. The Polytechnic School and my school, we are on the Mesa campus, or the East Mesa. It's about 30 minutes east of Phoenix Airport. And then there was a brand new school that was opened in ASU West, which is on the Glendale campus. All within the Phoenix metro area, not like all very far from each other, just 30 minutes each from each other. But this is how the school structure is. Very large school, 32,000 engineering students. My school is very small, about 300 students or so. But all, if you can see, the reason why the schools are organized the way it is just to look at challenging problems within the space of be it mechanical or chemical or material science or industrial and computing and informatics. Or biomedical, which is here, and then civil engineering, which is there, and electrical. The 3 biggest schools are computing, the mechanical, matter, transport, energy, and electrical, the 3 biggest schools within ASU. Okay, so that's the structure of ASU, and what our school is really about is this. I try to capture this in this picture here. You can probably see a lot of relevance for what you do as industrial and systems engineers within this concept of what the factories are being built today. So if you look at, you may have heard of in the news, TSMC is building up a huge chip manufacturing plant in Phoenix, in the Metro Phoenix area. Intel, with all the doldrums that Intel is facing through, they're still building fabs in Phoenix, next generation fabs. These fabs are sort of the most extreme environments you can think of, highly automated, highly data intensive, extreme quality requirements, extreme yield requirements, and that's just from the chip manufacturing perspective. But if you also look at the aerospace and the next generation of factories being built, if you just look at those factories, today these factories are not just standard robots anymore. They are smarter robots. Machines are now all interconnected. There is a level of computing that is happening at the machine. There's a computing at level at the factory level. There's computing at the cloud level. Then how does the data go? And then changes in the way the factories are even organized, even from a simple warehouse to an actual production factory. And so some of the next generation factories really encompasses all of these 12 technologies that I try to kind of capture in what the essence of our school is as well. Now, this is also within a factory, but you're now also seeing factory to factory also being network connected, which is why that networks is part of our school. It's not just the machines are connected, but also factories are also interconnected with each other. I won't go through all of these. Some of you are also relevant with some of the AI, of course, in the context of factories and manufacturing, smart robotics, cloud, fog, edge computing is sort of new architectures for how the factory is even organized, one of my research areas. I won't focus on that today. And then, of course, I'll talk a little bit of manufacturing marketplaces that I thought many of you will find it relevant. A little bit on the industrial Internet of Things and how things are all connected. So that's kind of really where the new factories are being built. Here in the US, they're highly automated, highly data-driven, highly integrated between the various physical systems and the virtual systems that make up it. Okay? Our school is about 22 faculty. As I said, we are a small school, about 22 faculty. We have probably the very unique combination of degree programs. We have, on the manufacturing track, probably the only school that has bachelor's, master's, and PhD in manufacturing engineering. Our BS manufacturing and PhD was all brand new, started this fall. Same thing with our robotics program, also brand new. Among the top 50 engineering schools, Michigan, Ann Arbor, and us are probably the only ones that have the bachelor's track in the robotics program. We had our first batch of students coming up. Just an exciting time for robotics. I think the US bought more robots than it ever has this last 2-3 years. So consequently, you're also going to need engineers who are going to work at the bachelor's level. Many schools have it at the master's level, but we have the bachelor's and PhD as our kind of, and then we of course have a PhD systems engineering. The newer ones is really what the uniqueness of what we do is really focused on that manufacturing engineering. So we are very still process-centric. We are still very process-centric. The students that come into our school need to get hands-on processes, which is why you also have new buildings that is going to be built up in fall 25. We'll move into this new building. But really more than just the building, it's what's inside that building that matters. Because one of the risks that ASU is taking is that manufacturing is coming back to the US. Hence, we need a lot more bachelor's and master's and students in that area. Question is high school students going to pick up a bachelor's degree? That's the remaining question, right? So hopefully a facility like this will hopefully attract a lot more students to look at manufacturing and look at industrial robotics as a potential career option, and companies seeing the value of it, right? And so if you can see some of the labs and the way we have organized a little bit of larger pilot open spaces, we are moving away from the concept of 700 square feet labs or 1,000 square feet individual labs to a little bit more shared labs between that shows the concept, shows pilots, test beds, a little bit more concept of industry working jointly with academia, where industry has a physical presence in this building. So we have it set it up that way. And hopefully, if you are visiting in Phoenix, I know the Informs conference was here last time, but hopefully more opportunities as this building comes up in this July. In the heat of the summer, we will move over to this new building. And just some of the highlights of our school. We are, again, it's a startup school, 22 faculty. Probably in a normal department, it's about the same size. But in the scale of ASU, it's a very small number. Most other schools are 100, 150 faculty. Engineering alone is about 420 tenure track and another 300 on teaching professor track or career track is what we call it. And we focus on the 22 faculty that we have a mix of manufacturing and robotics. Again, robotics and autonomous systems. As I said earlier, about 300 students, but just a more intensive effort in getting faculty into the physical processes and then data. And two areas that we're focusing on is how do you get manufacturing in extreme environments. I know some of that research is happening across other universities, but we intensely focus on, because we have robotics faculty in our school, it brings that autonomous systems very strongly into our focus. And so this is what our 3 areas are. So we focus our faculty. When I hire new faculty, or if you have students who are graduating from our programs, you have to be an expert in 2 out of these 3 areas, or rather be competent within 2 of these 3 areas. If you have all 3, great, but at least 2 out of the 3 areas, right? And so that's kind of what we are seeing as the future of what the next generation of manufacturing engineers need to be. So a lot of people do focus on materials and data. That's a common thing. But materials and robotics is also emerging as a way, especially in soft robotics or even biological robotics, in the context of manufacturing autonomous systems. And even machines that are also sort of more agile robotics is a sort of a concept. So our philosophy is that the students that we graduate and the courses that they take are in these 2 out of the 3 areas, if not all 3 areas, as a possibility. So what I want to spend is a little bit of contextual background in my research. You will see the research that I do is also fit into the context of what my school is about, although in the last 2 years, I would have to say my research took a little bit of a downward trend, but just because I'm focusing more on more administrative tasks, and not just administrative tasks, but setting the vision for the school and where we need to go. I'll talk about some of the concepts that I thought still have relevance even today, especially with the growth of AI. Hopefully you see relevance into the physical systems. That's what I keep telling all of the industrial engineers, all of the mechanical engineers. Find a physical relevance to the AI that you're doing, not just AI for the sake of AI. And AI in the context of physical systems are still a challenge. It's not solved yet. Companies are seeing potential for it, but how do you actually make it real? How do you make it economically viable? So we'll talk a little bit of that, and then I'll talk about a little bit of this concept of manufacturing marketplaces. Everyone has probably driven a Uber by now or a Lyft by now. That's a concept of a marketplace. We call it a 2-sided marketplace. I'll talk a little bit about that on the manufacturing side, what that actually means, and then hopefully some examples of future work. All right. So I take this example. This is my son, actually, when he was 7 years old. He's now 12 years old. I captured this concept, and he was drawing this on his iPad. So if you look at a 7-year-old child, clearly he hasn't just started going to school, right? Can he engage in product design? If you look at the way product is being designed right now, it is still done by significant experts in mechanical engineering, obviously, if it's a very complex system. But even if you take a very simple consumer product, you need to have the tools and expertise to use the software that is necessary for that thing, right? As a child would not be able to do that. Even a 12-year-old or even someone who's an adult who wants to design something in their homes, you can probably download 3D models now, but you can't engage in the actual making. In this case, it was a fire truck, right? Certainly, this child has a concept of what a fire truck looks like. He has seen other fire trucks, and he's drawing it on, let's say, imagine in the future, we might have a more smarter interface than the iPad, but then he is drawing it based on his concept. Today, we are not there yet in being able to do it. Today, you have sophisticated tools to design it, and rightly so if you're looking at aerospace systems or highly complex mechanical systems. But what about smaller, high, low-fidelity products? Or look at the concept of even how CAD is designed. Many of you probably use SolidWorks or Creo or CAD, Autodesk softwares in your undergraduate. You know, the way we design our products has not changed over the last 70 years or like the 30 years. I mean, if you say CAD, probably the 1980s it started, 1990s, 2000. Other than the beautification of the interface, the way you do it has not changed. And today you have chatbots and concepts of large language models being done, but again, not in the context of product design. We are still not there. And so today, can we talk to these systems to design products? For example, if I, as a user, were going to ask to design me a motor frame with a 2-inch shaft, I mean, a very nebulous term. There's so much details that go into that. Or even find me a bearing that is suited for food-grade applications, a little bit more specific. Even doing these kinds of things are slowly making its way, but you still have to put it in the context of whatever that you're designing. And so AI is still not there to be able to make these things. It can do search functions now. It can probably answer this question, find something, or tell me more details about it. But now if you try to ask it to design something, you still need to have your own expertise to be able to do it, right? Or even this question here, adjust the dimensions of a particular part and fit it into a 10-inch by 3-inch and a 2-inch bounding box. Now we're getting a little bit more constraints and examples that need to be like very contextualized to what is it that you're trying to do. So again, all of this will, if we were to solve this, then we create new interfaces for how humans interact with the CAD technology that has not changed in the last 30. Now, companies like Siemens and Autodesk are looking at ways to integrate large language models. And hopefully in the next 5 years, maybe we will see more newer, better interfaces coming through. And so as a motivational aspect of this is what has not happened is how do you democratize this knowledge of design? In manufacturing, when 3D printers came along, it democratized manufacturing. Right now, we have 3D printers in libraries. You had 3D printers in high schools. You were able to democratize access to making something. You didn't need a CNC machine anymore or injection molding. You could just take a 3D printer and you make that part. But what did not change during that transformation was the way you designed that product. Still, the tools were highly complicated that a child or a parent or someone non-technical would not be able to do. Today, how it's done, you just download to Thingiverse or go to some repository and download a model and 3D print on your 3D printer, which you can do. Or it would be like engineers like us who would design the products or industrial design experts, right? And so we haven't lowered the barriers to design and making of these products. And I'll give some other contextual examples after I show this example. So let's take the same example of the child drawing that fire truck in there. So the child sketches his version of a fire truck. He probably doesn't know all of the components that would go into a fire truck, but he kind of knows how that shape looks like. If AI was going to now search through all of the possible variations of these CAD models or fire trucks that were existing, either in videos or in movies or in pictures, it kind of understands what that concept is. And of course, it's integrating with what the child is trying to draw. And the child is, of course, drawing it on a 2D plane, and if this child has an intention of actually making it, the 2D is not going to cut it. You're going to have to make something that is actually 3D. So let's assume that AI was able to generate that 3D interface so that it's actually printable or makeable in some way. And then a parent would have to go into some sort of a marketplace-like scenario where that model is already integrated, and I just hit the build button. Most likely not going to be built on a regular printer at home. Maybe you can do it today, but most likely not. It's going to be sent out to a network of machines that have certain capabilities. Maybe it can do plastic parts, it can do metal parts or transparent parts, but it could produce that through a network of machines and then eventually sent back, right? As a personalized toy. Today we can do this, except that toy is going to cost maybe $10,000 or more, right? Because what happens during this, every one of those blue arrows, there is significant human input to making all of those arrows happen, right? And we saw COVID-19 come through, and COVID-19 disrupted the entire supply chain. We had a huge demand for certain products, a huge drop in demand for other products, and then the country was not able to respond to immediate things that it needed, right? So if we had a network of capabilities, and one of the things that the country did not know during that time was who had the capability to make what machines were owned by companies, what capabilities did manufacturing companies have. Nobody had a single integrated view of the entire, the US system at least, right? And so the government, if you're familiar with the Digital Manufacturing Institute, the MXD, the Department of Defense, even the Department of Commerce was resorting to manual forms to collect all that piece of information. In fact, that's how it was done in COVID-19. Who can produce which masks, who can produce the respirators, all that was done during that period of time, right? And today we still don't have a system that is able to capture that capability because it's not just about capability, it's also knowing which machine is available and when, right? And I think that is also a challenge to be solved. Right? And then now came the Ukraine war. And so the Ukraine war also stressed the system in the sense that the military could not produce enough artillery shells for what Ukraine was demanding. Right now, whether the Ukraine war, whatever happens to it, what that remains is fundamentally the country did not have the capability to respond to something where you need a quick demand for certain products and a certain drop in certain other products, right? How do you keep the system resilient to these kinds of changes? Now, I put this in the context of a toy. Not necessarily for toys. It could be even hurricanes that come through and affect entire supply chains. the country has to adapt or change, or huge demand for drones, or huge demand for artillery shells, or just one little thing that you would need. So how do you, and that the reason why it is not the ability to make it, it's these front-end arrows are still very manual and very, very labor intensive in how it is done. So I'll focus on we do a little bit of automation on this design, on this one blue arrow here, is how do you take that representation from even searching all similar functionalities for it. So I'll just talk about a little bit of a basic AI to be able to do this, and then how do you integrate the domain-specific text inside it. And I'll talk in the context of how we do this, not just pure machine learning, but some sort of an organization to it, is what we call as knowledge graphs in design and manufacturing, okay? And there's been a lot of work in knowledge graphs. Every single one of you is probably using knowledge graphs. If you use Google or LinkedIn, you're using it already. Or Amazon, you're already using it. But a lot of that is already mostly in the e-commerce space or in the people space, right? How do you bring it to design manufacturing? So this is kind of what is. All of you are using it right now. If you search for Michael Jordan, or if you search for certain specific movie stars, Google is able to find all related information because there is a knowledge graph that is running behind the scenes. Same thing with LinkedIn. It is able to create what is known as the people graph. If you use Pinterest, they use what is known as the taste graph. Movies have their own graphs, right? So every one of this is not just a pure search, but it's also interconnected pieces of information, which is how the panels that come up on the right-hand side is really what is powered by the knowledge graph. Same thing where Amazon, when you buy certain products, they have the related products come. That is also coming through the concept of knowledge graphs. And so what is a knowledge graph? A knowledge graph is simply, it's a graph-based data model that describes interlinked descriptions of entities, from objects to events to concepts, and then they all interlink them together. So right, that's what it's still a graph, but it's still beyond just a normal graph, but it is knowledge embedded in each of these entities and those nodes and arcs that form it. So this is just one example of a knowledge graph in a very small concept. So if I start from this side, it's a component. There is an arc that connects it to one component that goes into that assembly, and there is a relationship there. Each of these nodes have attributes associated with it. And then this node has, say, an HAS material node that goes into an aluminum alloy, then which is a type of metals, and that metals is a type of titanium alloys is a type of metal that then can be done in medical additive manufacturing. So if I wanted to navigate or search through this graph, and this is how the LLMs are also made more powerful now, is that they're not just purely AI, it's also working through this graph-based concept to find interlinked content. So if I wanted to ask this question, what different processes can I use to make this bracket? Because through these connections, I can actually identify additive manufacturing machines or other related parts that would go along with that part. Now, this is in the assumption that you can actually even create this graph. Most knowledge graphs, or the prior versions of this before AI came along, most of it was hand-built. People actually had to build that relationships, build that arc, build that connection, and organize it through some sort of an organized fashion. That's how it was typically done in the 80s, 90s. Google changed that a bit, where make it a little bit more automated. Now AI coming is also making it a lot more automated in what it does. So we wanted to build something similar, because I said with my fire truck problem, I still needed some way to kind of search these things. As in everything in AI, this was of course done almost 5 years ago, is where did all the data come from? So we had to collect and source the knowledge from where we had to get. We did collaborate with Stratasys, or if you're familiar with GrabCAD has an entire repository of 3D models. So we were fortunate to receive some sort of a donation of in-kind of giving us access to some of the 3D models. So we got access from there. Autodesk gave us a set that was typically not available today. Now it's all available. Had some relationship with Elsevier and some of the scientific papers. All we had to do was just take some of the abstracts and then some of the capabilities that were there in the manufacturing service companies. And so we sort of took all these different sources of data that we had and then tried to construct some sort of a graph that I will talk only about our 3D model data that came from our model repositories, but we have other work that we did a couple of years back on how we took this data and integrated it together. All right. So as I said, partnered with Autodesk and GrabCAD to kind of figure out a subset of data that we could use, right? And we have this shared all essentially. It's just a variety of different parts. You know, they didn't even know what they were giving us. They just downloaded or dumped an entire set of 2,000 CAD assemblies. And then we went through this process of cleaning out some of the models, some useless models, some models that didn't make sense, and then we wrote a script just to split that all out. Essentially, you had about 110,000 parts. We didn't know what those 110, we didn't see every one of those models, so we didn't know what it was. It was just 110,000 parts, about a terabyte of content, all different kinds of formats. And then we had some sort of a machine learning just to find some nuts and bolts and washers. But the rest of the stuff, we had no clue. You can just see the diversity of parts that were, some are standardized, some are non-standard parts. Okay? Clearly, there's a lot of duplication probably in this data. Like even, no one's searching through that 110,000 parts. And remember, our data set is so small. Companies like Siemens or Boeing has millions of parts in their database that have been built over time. For anyone to search the database would be an extremely complex task. But it has to be done if you're going to organize some of this data. So what we did was, and some of the older methods that people did for searching these kinds of things is through reducing the complexity of some of these models by tessellating them, putting it into a triangulated format, and then just did a simple search through the shapes for it. Things about in manufacturing, accuracy and precision are so important in what you do. Some other people, what they did was they voxelized the whole thing. No STLs or no triangulated formats. They voxelized the whole thing. But even if you voxelize it, you're going to lose features. And features are critical for certain important elements of it. What we did was, rather than voxelizing it or taking the 3D or the 3D triangulated representations, we simply took about 12 to 80 images of the 3D part. So basically rotated that part in multiple angles so that we don't get into a pattern-like format. So we were able to get 12 different or 80 different images of a single part and then ran it through a neural network just to capture what the essence and the relationship between all of these features inside this, and then ran it through. There was already a pre-trained model that the system already knew what lines and points and edges were. All we had to build on top of that and then pull through the data. We also did something similar where we're also getting some sort of a metadata like dimensions of the part, so there's some contextualizing around it. And then at the end, what we have to do, what we get is for every image, what you get is a simple vector with 1024 or 2048, depending on how big you want it. We got a 1024 numerical description of what this 3D part looks like, right? And remember, this is from 12 images, so that 1024 numbers represented what the 3D image could look like, okay? Remember, so we had 110,000 parts. We did this for every one of those 110,000 parts, and so essentially, this is a small subset of 10,000 models, and we asked the system to go and run through this model, and this is what 10,000 models and the connection between those 10,000 models look like. So every one of those dots that you see is one model, one part within that 110,000 or 10,000 parts here. So it should be 10,000 circles here. Every one of them is a 3D part. And then it automatically found, because you now have a vector, you can easily find similarity searches, and you can connect a similarity arc between two of these nodes. And remember, the nodes themselves have already attributes, for example, dimensions. If you have material, then you have material information or any other piece of information that have associated with that CAD model itself. All of that, what you're able. So if you see a little bit of a chunk here, what it means is that they kind of look very similar, and the system was able to find some unique components. Right? Same thing here, where there will be system, and there's some connection between some of the other parts. There's some similarity. If you zoom in a little bit more, so it's just a 10,000 subset. I couldn't put all 110,000 into one single thing, huge intense, but just to show the concept. And what you show is those links is really part of that graph, and the relationship is a similarity relationship. And you create what is known as, I don't know what happened. And so if I zoom into one particular node, what you see is, you will see that, there was a part that had a plate with square holes. I'm not sure why people design square holes into a plate, but someone designed it. And then what the system automatically then found, there's another plate with another plate that is also thin, And the system, oh, there's 3 holes in here and circular holes. Right? The system doesn't know what is what. All it showed was from that 1024 vector is that there seems to be some sort of a relationship between them. Same thing, you can define how many arcs it found. So you can see that very similar connections between just now a plate with 4 holes, another plate with too many holes, and there's a connection between them. There's another one here, there's another one here. Now if I take this even further, and so there's one little arc here, then now that is connected to another plate with 3 holes, but that is now connected to another plate with 4 holes, but there's a little slot in there that made it slightly enough different to be connected, not to be connected and make it similar to the other one. And then of course this has its own 10 other parts, so you can imagine this just going into an entire interconnectivity. In fact, you can connect all 110,000 parts through some relationship, but of course you have to prune some of the ones that does not meet edge criteria. But the point being is that if I were to now search for these parts, and if the system was wanting to find all similar parts that look like it, you can navigate this graph to kind of find similar parts. So maybe the person is looking for maybe designing this part and really probably trying to head to a part that is a slot. So now you have a recommendation as to, hey, maybe you're just trying to design this part, or there is an existing part that kind of looks like this. Maybe you just have to import this and not have to redo it from scratch. So that's what that search enables you to do. It is not a text-based search. You're doing a 3D search in some sense. It's not an image search either. It is a 3D search, a true 3D search, but that uses images to kind of capture the essence of the 3D model, right? And then so you can keep this going and kind of see what's happening. And of course, keep growing and it'll interconnect. You can start from here and navigate through this gap and then reach some other part based on what you're looking for. But inherently, that 10,000 or 100,000 parts, there's already product classifications around it. The system doesn't know that. The computer doesn't know that. All it's knowing is that there was relationships between them. So for example, here, there's this whole graph. I just highlighted a few. Somehow, it was able to find all these human figures inside it, and it found that there is something inter or similar about all of these human figure kind of 3D models. So you can find it. Now, if you were to search for okay, is there a human figure in my model? Now I already have a label. I can now classify that this entire cluster is human figures. So you could do this similar if you know what you're searching for and then kind of auto-label it. Of course, you have false positives. So for example, you notice that this truck here has a wheel kind of thing, and then, oh, it's found another connection. It looks like a snowmobile, right? How did that make that connection? The computer probably did not find other trucks in the 110,000 sets, but it found something that kind of looks like 4 vehicles or moves on there. Same thing, this has nothing to do with a vehicle. Oh, it found another one with a track in there, right? Some connection. Each of these arcs have a numerical value associated with it. Of course, it finds something else that has nothing to do with each other, right? And so this is where the issues come in, is that how really depends, of course, on how big your model sets are. But the point being that if this was 1 million models, you can scale this and just create an interconnected part. Of course, you can make it very intensive too, because remember, parts go very similar to each other. For example, a nut and a bolt go very similar to each other. You are not searching for the nut and a bolt. You can find other kinds of bolts, but not a washer and a nut and a bolt, they go together. So there's some sort of a class hierarchy going on. So you can find other sets of relationships in here, not just similar to, but more which 2 or which 3 parts go closer to each other. Like where do you see more commonality? For example, a wheel always goes. There are always 4 wheels that go next to each other, meaning then, okay, you probably need 4 wheels, right? Of course, there are ways to sort of clean this and make it organized a little bit better. It's just an example of just showing how you're just finding the similar to relationship. You can also do a functional relationship, which I'll show in a moment. But you can even see near identical parts. This is just parts of a chain link, so they kind of all look similar. So we know what we have to look for, and then there are very dissimilar parts, and you can just see the range from that 1024 vector. If it was a 2048 vector, it will be even more finer, but you're going to run a lot more computational power that would be needed. So now the question is, with just 110,000 parts, you can probably think of 12 trillion possible edges that connect through. Not all of them are useful. So how do you find even the useful ones out of these? And so there is a small but significant number of highly relevant relationships. So we've got to find that. And so you almost think of a sparse graph that connects all these different parts. So we only got 110,000 models, 1 million models, Boeing designs, mostly aerospace parts. So you will see a lot of commonality between what they do. Of course, they have 1 million components that go into a single plane, but there's still very strong relationships with what they do. And so there's how do you organize this graph through multiple hierarchies? So that's what we are trying to do, is also organize this not just based on similar relationships, but also look at ways in which to organize them based on a product assembly. For example, if you had this 3D CAD models, you would have all kinds of data associated with that 3D models. Is it a bolt? Is it a material? What units they are in? What functional characteristics that you have. If you have data such that we were able to store all of that. And then you have this relationship that, remember, we were given assemblies. So you already had a natural graph that connects between part to a sub-assembly to a larger assembly. And of course, it could go deeper depending on how big it is. And then you can connect them through through similarity relationship that I've shown. But you then also can create subsets through hierarchical relationships in there. And why that is useful is that, as I said before, there are parts that are very looking similar to each other. For example, springs. We see tons of springs and tons of bolts inside our head because people were building a lot of these standard components were in your design. So there was no need to connect with all different possible springs. So we were trying to organize this in a way such that I create multiple levels. So each of these, we call it what is known as a multi-level index that would go in. We call it hierarchical short graph kind of methods where very similar looking springs were brought together. And then that would go up to a next level, which is a little bit, they're springs, but not exactly each other. And then even more springs that don't look like each other. For example, now it's not this is a spring, but that is not, but it still had that spiral nature to it. So if someone were to search for springs, I don't have to waste my time. I need to get down to this level. I just can go to this first layer of an index. I can see there's a relationship here, then go down to the next level fast and not search through at the highest top level index. So I can prune some of my graphs and make it more faster in being able to search this, provided you have a hierarchy. And also it makes it useful, okay, if you're designing a spring, think of other springs that you can also be incorporating into your design. And so it very fastly be able to organize some of your data, right? And all of this is published, so you can sort of take a look at some of these things. The other things that we also were able to find out is, oh, wow, we have a lot of bushings in here, a lot of collets. So these are all standard part categories that you already know what the label for these are. Simply take a bearing and then just dump it into the model and or to this whole set and see how many bearings do we have and how many different types of bearings you have. And kind of organize your data rather than just a big bunch of data sets, right? And this is just all about searching and organizing the data. Where the field is headed right now, and we haven't seen much work yet to be done. People are still trying to figure this out, especially with generative AI that is coming through. The problem is all of the generative AI that has been shown so far is reconstructing the voxel structure. So if you have seen some of the papers that is coming out of Cornell or even OpenAI or even NVIDIA, all of it is reconstructing the STL or the voxel nature. Today you might see of NVIDIA Cosmos, you have all these 3D model assets where they've been generated. They're all void or voxel-based models, right? And then they create a wrapper around it. They're not CAD models. All that we use in product design, they're not STL models. Maybe for 3D printing, yes, but these product models have a graph associated with it. For example, like this, if you were to design in SolidWorks or in Autodesk or Creo, there is a BREP nature, a boundary representation nature to it. So you need to have a Gen AI method to generate the graph, not generate just voxels around it. And that also depends on looking at textual pieces of information. For example, can you generate a circular bottle cap with ridges on the side and with internal threads inside, right? And so I could probably use NVIDIA Cosmos to generate a 3D model that looks like this, but that is not how CAD model is used. CAD model is you need to generate the graph from it, right? And generating graphs is probably going to happen in the next few years, but it's also embedding of text and the 3D product models together, because this is textual information that I, as a designer, would incorporate and then put this through. Still a lot more work to be done. We haven't done much work in this, but hopefully some of the new PhD students, generative AI in the context of 3D. Again, all in the task of lowering the barriers of design. Searching and organizing is just the first step towards it, but hopefully also generating 3D models to make it easier to design next generation products. All right, so if you look at now the next problem, okay, let's say we have somehow designed this product, we have also even generated it, which we haven't solved yet. Now, where do I go to make these things, okay? So if you look at where do I go to make these things, today you could look at existing platforms that can do this. I as a designer, if I have certain budget for and how many parts do I want, I can go to some of these platforms like Plethora or Fictive or Exometry. 3D Hubs don't exist anymore, but Exometry and Fictive exist. Some of them have gone out of business. But the way they set up their model is they have a partnership network with their manufacturers. They know what their manufacturers can make. They kind of know some of the pricing structures. They do some sort of AI to even predict how much this is going to cost. And they kind of have this. So this is what is a classic two-sided marketplace that bring two sides together, hopefully based on the concept of sharing of resources. But what's missing here is there's an information asymmetry going on, meaning that these manufacturers do not know the identity of the designers. They also do not know the price that these designers are paying this platform, right? And so it brings such a case of mistrust inside your system. So they are not healthy in the context of a stable marketplace. So we call it, what if it was more decentralized, right? Well, there was a direct connection between this designer and the supplier. And all that the platform does is to bring those two parties together. I don't know if you know of a concept of a marketplace. Anyone use Etsy, right? Etsy is a perfect example of a decentralized marketplace. All they do is take a transaction cut, but you know who built it. You know exactly what the price you're paying, and Etsy takes a cut. So how do we bring that to manufacturing, which is not easy to do because it's not the exact same model where you can just take Etsy over and port it over to manufacturing, which is what these companies were trying to do, and they haven't figured out exactly the economics behind it. And the reason being is that manufacturers are a little bit of a different animal altogether than just your Etsy contributors. They have a business to run. They have a cost associated with it. So if you want to create a decentralized marketplace, you need to incentivize these suppliers to join your platform in the first place. And then you need to make sure that there's value created for these suppliers because they are giving you a piece of information. For example, I can do this part. I have this capacity. They're probably also even sharing their production schedule or their future production schedule with this platform so that when a designer comes, they know what excess capacity they have. But how do you bring them all together so that you can keep the system stable? So this gets into what, a lot of what we do in supply chain, but slightly different. Uber does this when you go into an airport and get down to the airport, you call your Uber. Uber does that on a small scale because all they have to do is worry about the drivers that are inside that local market. Here we're talking a little bit more complexity because in Uber, all you need is a taxi. You go to A to B, and then you can solve that problem. This is a little bit more different because the complexities of this order is a lot more. There's this material, that material, multiple options of materials, different prices for those materials. And so how do you keep, and then the capabilities are also different on the other side. It's not just like a car moving from A to B. There's different capabilities, different precision, different quality requirements, and so on. And so what we are trying to look at is to understand what are the stability constraints that make actually those marketplace companies to bring together. Because if I bring a fire truck as an example, if I don't have manufacturers who can make it, then you can't make it at the end of the day. I have my 3D printer, I can make it there. And there's a lot of work already done in this two-sided marketplace as a concept. Along with Uber, cloud computing as great examples of two-sided marketplaces. We see, there was only one work from Purdue that does some resource allocation, but they did a very simplistic model concept. A lot of in college admissions, kidney exchange. This is a field of what is known as computational mechanism design, not computational mechanism from the mechanical approach, but from the microeconomics approach. So it is a microeconomics problem where you have to incentivize participation from suppliers in the context of manufacturing. And manufacturing, as I've talked to some of these people here, more complex than just simple even kidney exchange or college admissions. So I'll just briefly talk about the problem in the interest of time. just to kind of see, and this is not a problem that has been fully solved in the sense that a lot more AI coming into it that you can make, and hopefully I'll introduce some of the terms that maybe there will be extended work here. So one, in a design supplier kind of perspective, it's different from an Uber. When I do an Uber, and a driver is allocated for that particular ride from A to B, right? There's no other orders coming during that, most likely until they lost multiple people coming. But you do have a many-to-one matching. There's multiple designers could go to the same supplier. There's a utility. This number here detects the utility of that connection, so there's a value associated with it. And then multiple designers, so there's a many-to-one matching. There could be multiple contracts between a supplier and a designer pair. So it's not just one order going. You could have multiple types of orders between D2 and S2. You could have designers, D1 and D2 have one contract each with suppliers S1 and S2, and design in D3 has two contracts. So the complexity of how you're matching in a manufacturing two-sided marketplace is a lot more complex. Okay, so now you can define what is known as stability. Stability is a microeconomics term to identify that marketplace needs to be stable by people who are participating actively in the system. Same thing as drivers. Uber brings a lot of drivers into the system to make sure that there's enough drivers for demand. So it's kind of the same thing. But the difference here, of course, is you want to make sure that the system is stable, meaning that a supplier, once they accept the order, they need to know that they're getting the maximum value out of that, not just, hey, I just lost value in this, right? So you want to the system needs to make sure that there could not be another order that this person could have received, right? Because if that happens far too frequently, the suppliers will just leave the system. They're not seeing value in it. So you've got to make sure that the system is stable. And there's in the concept of microeconomics is what is known as a blocking pair, right? You don't want to see that in a system, oh, initially I assigned them D1 to S1 and D2 S2, but you know what? If I had connected D1 and S2 together, there would have been a lot more value. So now that's blocking the value that would have been created otherwise, right? And this, remember, S1 and D1 is rotating, right? It's not just a constant stream of the same D1s and D2s coming. They come in and out of the system, same thing, S1 and S2 and S3 and so on. They come in and out of the system. So the concept of group stability as well as individual stability is also looked at. And then there's a concept of posterior stability and transient stability and posterior stability. What is transient stability? Transient is there's a group of suppliers and a group of designers that have come during a period of time. You can define that period of time, 24 hours. And you want to make sure that the right matches have taken place. But you know, as a driver, if you're ever driven for Uber, should I accept this order or not? What if a better driver, what if a better ride came later on? So that's the same thing with the suppliers. This S1 is making a decision whether to accept this order from D1 or should I wait to the next period to kind of hopefully maybe a better order coming in. And that's called posterior stability, is that after the next period and the next period after that, that you want to be sure that you're giving maximum value to this S1, that there is no better order coming to you next time because it is the best order that you're going to get. The system has to ensure that. And right now, many of these companies are failing because they are not able to ensure this from a stability point of view. Okay, and then there's also concerned with the utility, right? You want to get the maximum. Once you create a match and a stable match, you want to make sure that you also got the best business possible and that you don't have to go outside the system. The other thing about these manufacturers and why some of these companies are failing is that there's not a whole set of suppliers. Once you know the identity of a manufacturer, then I don't need your platform. I can just go directly contact the company and do business with them. That doesn't, if that were to happen, then there's no need of a platform. In Uber, you never do this, right? You never contact the driver later on if you happen to come to the same airport. You don't contact the same driver. There's no need for you to do that. Same thing here. Here, people do contact. That's the issue because now I found a new supplier. D1 knows the identity of S1. And why do I need this platform? I just go directly contact you, give you the business, forget this platform, and kind of do that. And so the platform also has to ensure that the value by coming to the platform is more useful. And that's what we capture by the utility. So we went through this process of looking for stability as one criteria, and then utility as another criteria, and even figuring out how the policies actually work between creating this contract. So there's a contract here between I, J, and then the C is the value of the contract that is between those two parties, and you got to figure out in every period of time who are the matches that would come in. Just like Uber is matching your drivers at that same time, notice that when you click on the confirm match, it waits for a period of time. It's running that optimization routine between to find you the best driver. Same thing that would have to happen here, although it's a lot more complex because the driver, or here the designer, is looking for other things, not just the part. And so you could create equations that simply minimizes the blocking groups. Each designer is match most ones, and the compiler can accept one set of orders, create stability constraints in that sort of scenario. Also, sort of skip through. You can certainly look at the paper that was just described this. So again, a lot of different ways to do it. One, you can do it the standard way of approximately, the maximum weight, which is just maximizes the utility. Forget if they have, you're ignoring stability in the platform, right? Even if they contact each other, that's okay. You've got the prompt. That's one extreme. Or the approximately stable, which is it focuses on stability, but doesn't maximize the utility of the contract. Or you could do somewhere in between. Just to share we did a simulation run through it, and what we have seen is, what you want to minimize is, you want to get this to as minimal, like number of participants in a blocking pair. You should not find two participants that really did not do business, shouldn't be doing business with each other, but you ended up giving them business. And you want to minimize that as much as possible, because if you have more of that, people will eventually leave the system, and you won't see a stable marketplace. Right? And so what we're trying to show here is that you have to get somewhere in between this. Now, again, this was all done simulation-wise, which is why we don't know from a theoretical standpoint. We got to still prove that these were indeed achieved stable. And that's something that we have struggled with, trying to figure out how to show that it is stable with all the sets of participants that are coming through. The other thing that we were also able to show is that if the system participants were constant in the system, and many of these companies that I showed why they fail is because they don't reveal the identity of who supplied the part. That becomes a huge problem, because eventually these designers are going to know the identity of the suppliers. And then the value of using that marketplace or platform doesn't become valuable. Right? And so what it's also telling you, the system is also telling you that you shouldn't be waiting way too many days to figure out the period of days. Match the system and continuously put more designers or more suppliers into so that you have a rotating cast of people coming in. So that way, even if you reveal the identity, it doesn't really matter. You have the best price possible from utilizing your platform, right? So lots of, again, a lot more work that needs to be done. There was also another paper that we produced on how do you even learn from the system by, okay, you created a match between a designer and a supplier. Did you learn something from it that hopefully a better policy is created later on, so you can use some reinforcement learning approaches here, okay? And eventually what we are trying to do is, again, just small aspects about this problem. At the end, what the DoD and even Department of Energy and Department of Commerce is looking for highly stable, resilient networks of manufacturing warehouses with various capabilities, so that when the country needs something, that there is a way to kind of source these materials. That's the larger problem that we're trying to solve. In fact, DARPA has programs in this space now in terms of, even NSF, we had a regional innovation engine. How do you bring remote areas also into this manufacturing concept in here? Right, and I did not define what cyber manufacturing is, right? So that's why I wanted to share this at the end. What is, at the end of the day, cyber manufacturing? If you looked at the example, we are using shared use of network manufacturing infrastructure. Those suppliers are coming to the platform because they have idle machines sitting in their shops. If by donating, or rather contributing the capacity of time, you're having now a shared use, so that designers don't have to have their own machine shops or have to get their own things, right? And so you're maximizing utility, reducing consumption, and all sort of digitally connecting all these network sources, right? Part of this is also not just about what I showed in the marketplace or the AI search. Generative design is also an important element. There's also factory network connectivity that's also important. So one work that I have not shown you here is also we are working on systems to actually connect a real physical system to a virtualized version of it. So that this is an example. This is a virtual CNC machine on the NVIDIA platform. But how do you take real-time data coming from the actual physical machine and make it move at the same time? and do you have to move all the data through your clouds, through the systems here, all the way up to a cloud that comes up here, right? So this is one example that we are working on, using industrial protocols, even reframing how the industrial protocols are written at the factory level. Because right now, most of the factory information architecture are very old, 35-year-old architectures that don't make way for the AI system. This is another example of a reverse method where we are controlling the we are controlling the virtual robot, and then the physical robot moves automatically, right? So you can virtualize, or rather move it virtually, and then physically it moves in real time, almost near real time, right? And so that enables teleoperation from a manufacturing context. And again, there are a lot of technologies that to make it move from the virtual. Now, I showed the example of just one machine, one robot. But think about it, factory has hundreds of machines, and whatever you might show in a one machine doesn't really show scalability unless you show that with multiple machines running in a factory. Right? So again, small examples of this. We're also working with fully autonomous manufacturing, meaning that the programs are not, the robots are not working by programs that are written, but autonomously generating the code necessary to show examples of it. Eventually, if you're going to ever build in space or build in Mars or anywhere it is, you have to have these autonomous systems to kind of regenerate code and not have AI just fail there at a particular point and then nothing can be done, but it has to self-correct itself, right? So a lot more uses for that. We also are introducing the concept of gaming into our school, sort of using games to kind of teach manufacturing, so it lowers the cost for ASU and even broadcasting manufacturing education. That's one of the challenges with manufacturing education. It's very expensive because of the infrastructure and machines and costs you need. So can you use concepts like the games or concepts like the virtualization of it to create more innate experiences for students, right? So with that, I know a little too much over, but again, I want to thank a lot of the students. A lot of my students have chosen not to go to academia, but rather go to companies. And so many of them who have worked on the technologies they're either going Deloitte or they've been in Dow Chemicals or Micron, because a lot of these technologies are already slowly starting to make its way into companies. And a lot of opportunity there for companies as PhD students to work in these areas. So again, thank you for your attention. Happy to answer any immediate questions. Thank you.
Any questions from the audience?
So in the 3D modeling and the search work, is for traditional computer-aided manufacturing, we have a grouping technology. Mm-hmm. So we can add the material, the way we fabricate that part into the code, into the final code. So, but based on the deep learning network, based on what you presented, something like you mainly care about the geometry. So can we add the material or the way, the manufacturing or the tolerance into the
knowledge graph and search? Yes, yeah. For sure. We did not do that because we know we could do that. That part of the work already is there in terms of group technology. Remember I said each of those nodes have attributes underneath it, right? So when the knowledge graph is being formed, one way is to connect them through similarity graphs, right? But you don't have to work through similarity. You can connect it through functionality, as I said. But when the connection is happening, you can accommodate for the information that you have in each of those nodes to make that connection, right? And so that's what, so we don't have access to those systems. So Boeing has access to their systems, or Airbus has it. Automotive companies have that. The concept is that the machine learning code is not just working on geometry. You can embed text into the search. Today, the technology already exists to embed that text along with the geometry to build your graph the way you want it. And so these graphs are dynamically generated, right? That connection between two parts exists based on the context of what you're searching for, right? So if you're searching for similar looking parts, sure, you can get similarity maybe the way you're looking at. But if you're searching for, give me all parts that are related functionally to this engine component, then that's the search. That's based on the attributes that go through it, right? It's not based on similarity at that point, right? Similarity, the shape part of it was the more complex part. The text is actually the more easier part to handle.
Yeah, thanks, Binil, for the great talk. So I have one related question. It's about the data source of generating these kind of geometry bank or part banks. So are there some insights about how to access this kind of data, and also what is the data representation? Are there in the form of point clouds or some other open source or widely accepted formats of representing these shapes?
Right, ever since we did this work, as I said, Autodesk had given us some data. At that time, they had not publicly shared the 3D models. But now if you go to the Autodesk 3D shape gallery dataset, they have an extensive collection of parts. Prior to this, there was Karthik Ramani at Purdue University that had certain categories of standard parts, right? This had non-standard parts. Non-standard parts is the harder part because you can use GT and other kinds of technology to do the standard parts. That's not the challenge. The challenge is the non-standard parts. So how do you represent the non-standard parts? Right now, if you look at the Autodesk gallery or in the GrabCAD gallery or even our data set, we have publicly shared our data set too, is that they're still in the raw format of the 3D model itself, right? So which is be it a BREP or a step file. That's it. Step file is all that is representation. But when we put this into the graph, we take that 3D model as long as also with the attributes, whatever attributes are available to it. We got it from GrabCAD. Autodesk gave us the public data set. Most of it is incomplete information, right? But if you get core access to a company, for example, Siemens data, they have a lot more information available to it. And that data is organized in the form of a graph in itself. And how best to represent it, we don't know. Again, unless you have access to the data, there's no way to kind of look at it. But I know there's work done within Autodesk R&D and Siemens R&D. They are doing that because they have access to millions and millions of data. And the way to represent this data is not your standard way. You don't put this in a standard database structure. There are specific graph databases for how you represent. So this knowledge graph that you see there, it is also on a graph database. You can't just represent it on a normal document store or SQL structure. But a lot more work still needs to be done on how to represent the data for enabling these kinds of things. Right?
Have you done this kind of thing not only for parts, but also for machine side? I think that's also
possible. Yeah. I mean, if you can do this with parts, you can do this with machines too, right? Absolutely not a challenge too, right? But that's assuming you have access to the machines, and that's why I was showing the other work on that was where we were heading to. Is once you have the virtualized representation of a machine, then you can work with the vendors of these machines to create what a representation of that machine could be. And the capability of a machine changes over time, right? Today you buy this machine. It has certain capability. Most of it doesn't change, but eventually the accuracy slips or certain things need to be accurately captured over a period of time. The other thing that you also have to capture about it is, for a company's perspective, is just because you have $1 million machine, sure, you're capable, but are you fully capable to deliver the part that I'm asking you to deliver, right? That also needs to be represented, and that can only be captured by looking at the historic parts that the company has produced prior to receiving an order. So where do you get that access to data, right? So those are important challenges that even DARPA is asking us to figure out how we might find what the capability is, one node of that manufacturer is, over a period of time, so that you can predict what future capability they will have, right? Yeah. Technical capability, right? So into making a part at the level of precision needed.
Thank you.
Yeah. I think we can take other questions offline, but let's thank the speaker again.
Thank you.